we'll just start recording, and then we'll post this on our YouTube channel and advertise it through social media platforms later on when it's available. And thanks so much everyone for joining today's webinar for ISL Brownbacks. As you know, like Brownback is a platform where ISL is really advertising and also is promoting our effective police research. So today we're very, very happy to have Dr. Qianwen Guo joining us as a presenter with her graduate student, Daniel Aldawi. So Dr. Guo is an assistant professor of transportation engineering in the Department of Civil and Environmental Engineering at FSU. Her research interest focuses on transportation systems, optimization problems, especially in public transit, shared mobility, mobility, transportation resilience, as well as transportation economics. Dr. Guo is a member standing committee on transit management, transportation research board, National Academies of Science, Engineering, and Medicine. Dr. Guo is also active author of journal publications, conference proceedings, and technical reports, as well as an active collaborator on research projects, mentorship, and professional leadership. She has published more than 10 papers on a wide range of research topics as a first author or corresponding author in renowned transportation journals. And she has also several ongoing research projects sponsored by National Science Foundation, Florida Department of Transportation, U.S. Department of Transportation, USDA. She was also featured by Society of Asian Scientists and Engineers on the 2021 World Engineering Day at FAMU-FSU College of Engineering. Prior to her current appointment at FSU, she was an assistant professor at Florida International University from 2022 to 2023. So please welcome Dr. Guo for the presentation with her graduate student, Daniel. Dr. Guo, please take over.
Yes, thank you so much. Good afternoon, everyone. It's so wonderful that being here at the Institute of Successful Longevity. This is the place where we don't just talk about the living longer, but also living smarter. My name is Qianwen, or Vivian, if that is easier. I'm working on the Florida State University. I have a research lab, it's called a Smart Transit Lab. And today I will taking you a little ride, quite literally, through the world of accessible public transit for elder adults, powered by the content inspiration. So this will focus on how we design public transit system that can better serve elder user, while maintain the efficiency and scalability, and how content-inspired optimization can help us achieve that balance. Before we get rolling, let me introduce my little research family. Daniel, he is my doctoral candidate, is the brain behind most of the coding magic here. He has been studying at optimization equation for so long, and that he sometimes answers questions in binary. And my collaborator, Dr. Raymond Kerr from RPI, the content mind behind our content inspiration. Unfortunately, he could not be here today, but if he will be probably explain some qubit with passion that we will start all seeing bus route in superposition. I would like to acknowledge his contribution to this research. So what do we do in the Smart Transit Lab? Well, everything that keep buses, bridge, and brains working in sync. To give you a better understanding of my prior research, I would like to start by providing the overview of my research program. My work spans several key areas within the transportation system optimization. For example, I have explored how government can regulate and subsidize transit operator, ensuring that public transportation remain efficient and accessible. Additionally, I have developed travel incentive scheme aims at encouraging public transport usage and nurture the dynamic coupling participants to adjust their predetermined travel schedule for a greater efficiency. So this study has been published in the Leading Transportation Journal. As you see, we are quite busy teams out with FDOT, NSF, USDA, and even USDOT. We are like the avenger of transportation. Each agency brings a superpower. I have been fortunate to lead and complete several research projects in recent years. one of my recent complete projects sponsored by the Florida Department of Transportation that's working on evaluation and a validation technology option for estimate the transit occupancy in real time. This project aims to evaluate the current technology available for transit vehicle occupancy. So given the diversity of the Florida transit system, the project found that the IoT, Internet of Things, Wi-Fi technology can provide a cost-effective way for monitoring transit occupancy in real time. In addition, I led a project focused on building a digital twin-based visual reality lab for students with disability. This initiative aims to create an inclusive learning environment by utilizing the digital twin technology to enhance the engineering education. I'm also working on projects that evaluating the feasibility of utilizing the large-scale linear resource document and evaluation as the mitigation measure for the FDOT. And I also lead one project funded by the National Science Foundation. This research propose and evaluate an innovative scheme for the food distribution in food desert area, as our Panhandle area considered as the food desert area. We leverage advanced autonomous vehicle technology, such as drones and autonomous vehicles, robots, with implementing the coordinate the food delivery system that effectively combine the traditional vehicle ground transportation and autonomous robots. We can achieve the significant cost saving and society economic benefit. So this project reflects my ongoing commitment to advance the transportation system and ensure that our research lead to a practical, innovative solution for diverse community. Here is the roadmap of today's talk. We will study with the why, aging, and the mobility, then move to our model, how content inspiration sneak in, and what result we can find, and finally, what it all means for building a more accessible, inclusive transit system. So we will go grand challenging to grant the solution. So let's begin with the introduction. We will start studying with some fun facts here. By 2050, 1 in 6 people will be over 65. That is not the future, but that's almost the near route change. And over 40% of seniors already report mobility limitation. That is a serious reminder that transportation isn't just about efficiency. It's all about dignity, independency, and staying socially connected. In fact, studies also show that improving accessibility could increase the senior transit use by about 25%. So that's what I call a return on empathy. So the challenge we face is that traditional transit route design model mostly focus on the minimizing the cost or travel time, which might make sense for an efficiency standpoint. But what about the human side of the trips? Empirical study on the travel behavior show something fascinating. Passengers actually place a much higher penalty on waiting time, walking time, and transferring time on the time they spend sitting comfortably on the bus. So, reducing these access-related burden, like a walking distance, waiting time, awkward transfer, can be just as important as reducing the in-vehicle travel time itself. So now, while focus on the efficiency is good for the budgets, it often comes at the expense of accessibility, especially for elder users. The key accessibility factors, such as walking distance, stopping space, and the service coverage, are rarely optimized alongside efficiency goals. So the research shows the gap in service, and many seniors love a long, uneven, safe walk just to reach a transit stop. And to make things more interesting, classical optimization model tend to freeze up when we ask them to balance the multiple conflict objectives, like minimizing the cost and maximizing the accessibility and maintaining the coverage. So there is a tall core order for the traditional algorithm. So to truly design transits for all ages, we need a smarter and a more flexible way to judge all these priorities at once. So that's where our content-inspired bi-level optimization framework comes in. It allows us to efficiently balance both accessibility and route efficiency without compromising one for the other. So a quantum computer is fundamentally different from the classical computer we use every day. Instead of using bits that are either 0 or 1, quantum computer can use bits which are based on the quantum system and can exist in multiple states simultaneously. This ability comes from two key principles, where the superposition and the entanglement. In superposition, a qubit can be a state of 0, 1, or both at the same time. This allows quantum computer to explore many possible solutions in parallel, rather than one by one. While entanglement, qubits can be linked together, such that the state of one directly affects the state another, no matter the distance between them. So this enables the powerful correlation that classical systems simply can't achieve. On the right side of the slide, we have a visual of the block sphere, which helps us represent the states of a qubit as a point of the sphere. So depending on its position, the qubit can be in various combinations of 0 and 1 states. So what does this mean for us? Well, computation flexibility made quantum computer very suitable for complex optimization problems, like the one we face the network design. There are problems with involving mass, search space, and interconnected decision. And so this problem can be approached more like efficiently using this quantum algorithm. To better understand why quantum computing is so powerful, it helps to compare it directly with the classical computing. So we have the classical computer, the kind that power everything from smartphone or the computer. Its basic unit of information is the bit, which can only exist in one of two states, 0 or 1. These are the typical stored using the transistors or the magnetic memory, so they can measure a classical bits. It simply gives you the value that you can set, meaning that is deterministic or predictable. We have the quantum computer, which use the qubits, and the qubits can be in a superposition, meaning that they can be in a mix of 0 and 1 simultaneously. So when you measure the qubits, the outcome is a probabilities. So you might get 1 or 0 based on the aptitude in the superposition. For instance, the qubit is evenly balanced. There is a 50-50 percentage of getting either result. So this ability to process many possibilities all at once and work with interrelated entangled states make the quantum computing extremely promising for solving large-scale problems. Also, since a classical computer, information is stored in bits. If you have n bits, you're only working with one possible combination at one time. For example, if n equals to 3, you might processing 0, 0, 0, 0, 1, or 1, 1, 1 out of all a combination, but only once of those at any given moment. Therefore, to evaluate all possible configuration, you need to rerun the computation multiple times, one for each input. That's why we refer as a classical parallelisms, especially performing many separate calculations, one after another across multiple processors. Now, compare that with a quantum computer with n qubits. The system holds a state that are superposition of all 2 to the power of n combinations simultaneously. So instead of needing to run the computation separately for zero,
I know I can tell you about these 2 projects I got from me and you. Because you've been.
The quantum computing can let us process them all at once using that called the quantum parallelism. So this is exactly the kind of speed up we want when deal with the large-scale transit design problem. For example, deciding which stop to activate or where to relocate the stop to best serve the elder user. Quantum algorithm can evaluate thousands of possible route and stop configurations simultaneously. It allows us to find a highly efficiency and accessible solution much faster than the traditional optimization methods. So now to talk about the kinds of problem quantum algorithm actually speed up and by how much. So this table outlines the different types of problem comparing the classical computation time with the quantum time and showing the potential speed up we gain. We won't go through all of them, but linear system, which we often encounter engineering and optimization, quantum algorithm can deliver the explanation speed up, but only under specific condition, like having a sparse matrix. When it comes to the optimization, it lies at the core of this research. Quantum computing can provide significant speed up, and especially for problems like the transit route design. However, in optimization, they are not just one to define a good answer. Sometimes we are not necessarily looking into the best, single best, or global optimal solution. Instead, we want a high quality solution that is close enough to the optimal and obtained much faster. That's why quantum approach like QAOA, quantum approximate optimization algorithm, can be powerful. They explore large decision space efficiently and yield a solution that balance the quality and the computation speed. Additionally, in classical computing, a search through a database typically takes a longer time, up to n steps to find the target time. However, with the quantum computing, the search time is reduced to the square root of the time in which the fact is a significant polynomial speed up. So highlight the contribution of the work. So this is chart showing the elsewhere showing the numbers of the published document publication on the quantum computing from 1983 to recent 2022, as you can see. Interesting remained the model until the early 2000. And since then, especially post 2016, we've seen a dramatic surge. So what this means is that in recent years, the numbers of publications has more than doubled, signalizing that the growing investment for both academic and industry, and increasing accessibility to real content hardware via the cloud platform. So has been a shift from the theory to application. Therefore, quantum computing is no longer an abstract future technology. It's a rapidly growing field with the real tool and real-world relevance, especially in domains like transportation, logistics, and disaster evacuation management. Even the optimizing and the decision-making are critical. So the main contribution is that development of the quantum-inspired bi-level optimization framework designed to improve the both accessibility for elder user and the route efficiency for transit agency. In other words, this framework bridges 2 priorities that often at odds, like social equity and operational performance. We achieve this through a hybrid content classical approach, where the content approximating optimization algorithm is used to efficiently solve the routing subproblem at the lower level. So this integration allows us to explore a very large decision space, evaluating the possible stop and the route configuration, while maintaining a realistic focus on the service coverage and efficiency. So I will leave to the following the slides for my PhD candidate Daniel, who will continue to present it. So Daniel, you can share your slide. Yes. We can see your screen. You just mute yourself.
Okay, so thank you for the introduction, Dr. Guo. I would like to continue from this section, which it's the literature review. So just a quick review of the existing studies and emerging trends that shaped this research. I would like to highlight the key work on accessibility for older adults, bilevel optimization in transit planning, as well as the growing interest in quantum-based optimization. So several studies have shown that older adults rely heavily on public transit for essential trips like healthcare, shopping, and social visits. However, accessibility barriers such as the long walking distance, unsafe sidewalks, and the infrequent off-peak service often limits the mobility. And we also have research that highlights that a walking distance of 400 meters or less and appropriate stop spacing are critical for encouraging senior transit use. And then we have features like ramps, barrier-free paths, as well as design stops that can, significantly improve the perceived accessibility. So these findings underscore why accessibility must be a core design consideration in any transit planning model. And then we have bilevel optimization, which has become a valuable tool in transit planning because it can capture the hierarchical nature of real-world decisions. So at the upper level, planners or policymakers can define accessibility goals, for example, reducing the seniors' walking distance, while at the lower level, we could consider something else like the operational efficiency, optimizing routes within the given constraints. So we have studies like Chen et al. 2020 and Calvert et al. 2023 that demonstrate how this structure can balance user needs and agency objectives. And then we also have recent work, including ours, that also explores like equity, efficiency trade-off, acknowledging that extending routes extending routes to reach more elderly users can, slightly increase costs, but it leads to fairer service coverage. So recent studies have shown that quantum and hybrid optimization methods such as QA/OA and a quantum annealing can efficiently explore complex routing problems. And these approaches have already been applied to transportation challenges like vehicle routing, scheduling, and traffic flow optimization. However, the current limitation is that most models remain computationally heavy and don't scale well to large hierarchical problems. And more importantly, none of them explicitly focus on equity or elderly accessibility in transit planning. So this reveals a clear research gap, which is sort of the need for scalable frameworks that can preserve that hierarchical structure while directly addressing accessibility for older adults. And that's exactly what our study proposes. So now that we've talked about the research gap, I would just like to quickly move to the methodology. In this section, I'll explain how the study was structured, beginning with the bilevel formulation, which links user accessibility and route efficiency, and then the quantum optimization problem that helps solve the routing problem. So this figure illustrates the baseline configuration of our study area. The orange circles represent existing bus stops, and the red triangles mark age-restricted communities, which are essentially neighborhoods with a higher concentration of elderly residents. So each of these circles here shows a 400-meter walking buffer, which is the maximum acceptable walking distance for seniors based on findings in accessibility studies. So as you can see, these bus stops fall outside these buffers, meaning that seniors in these areas remain underserved. So our objective is to adjust the route between the stops A and B to improve accessibility for these communities while keeping the route efficient. So for the bi-level optimization model, at the upper level, the decision maker remains the senior users, and the objective essentially is to maximize accessibility by minimizing the walking distance to nearby stops. So the key decision variable here is ZKI, which determines which community is assigned to which bus stop. And then at the lower level, we have the transit agencies, which are the decision makers here. So their goal is to minimize the total length of the route segment. And the decision variables here are YI and XIJ, which define which stops are selected and how they are connected. So these two levels are connected and they are interdependent. So the upper level improves accessibility while the lower level ensures route efficiency. So in this framework, the lower level routing problem is solved using our quantum-inspired approach, while the upper level is handled through a classical optimization method. So we created a hybrid system that balances both objectives. Before going into the formulation, just a quick overview of the symbols and variables used in the model. So on the left, we have the spatial and the distance parameters. For example, xi and yi are the coordinates of each stop, while dig and dki represent the distances between stops and between communities and stops. Then the parameters dmin and dmax define the minimum spacing between stops and the maximum allowable walking distance, which in our case, we considered 400 meters, just as I said earlier. Then on the right, we have the decision variables that drive the optimization. So all these variables determine how the route is formed and how accessible it becomes for the elderly users. At the upper level, the model represents the perspective of elderly users. And once again, the objective is to minimize the average walking distance for each age-restricted community to its nearby active bus stop. So this is expressed mathematically as the minimization of the weighted sum of distances, dki multiplied by the route segment, zki. And then we have constraints because every real-world problem is constrained. So each community, one of the constraints is that each community is served by exactly one bus stop and that the maximum walking distance does not exceed the acceptable threshold, which we set at 400 meters. And then the communities can only be assigned to stops that are actually active in the network. And finally, that all assignments are binary, meaning that a community either uses a stop or not. So together, these constraints ensure fairness and accessibility in how the bus stops are allocated to the senior communities. And then at the lower level, the focus shifts to the transit agency's perspective. So the goal here is to minimize the total route length, thereby keeping the system efficient. So the objective function minimizes the sum of the distances dij multiplied by the routing variable xij. And then we also have several constraints at this layer. First is that each selected stop has exactly one outgoing and one incoming connection. And then the total number of stops is fixed, which maintains operational consistency. Then we have that the maximum route length cannot exceed a tolerance factor of delta multiplied by the original route length. And then we have the maximum and minimum distance constraint, which ensure that the stops are neither too close or too far apart. Then we have the subtle elimination constraint, which prevents disconnected loops. And then finally, we have that both xij and yi are binary variables, which so defining whether a link or a stop is part of the route. So in essence, this level ensures that the route remains efficient and connected, complementing the upper level goal of accessibility. And then we can take a look at how the quantum approximate optimization algorithm, or QAOA, is integrated into the framework. So on the left, we start with the optimization problem, which is reformulated into something that is called a quadratic unconstrained binary optimization model, a QUBO model. And this step expresses the objective and constraints in quadratic form and then converts it into an equivalent Ising Hamiltonian that a quantum computer can process. And then in the center, we have the QAOA circuit structure. The algorithm alternates between two operators, which are the cost Hamiltonian and the mixer Hamiltonian. The cost Hamiltonian, HC, encodes the problem itself. And then you have the mixer Hamiltonian, which explores different solution. So at each iteration, we adjust these parameters, beta and gamma, to minimize the expected energy, which effectively improves the solution over time. And then we have the execution phase where the QUBO is mapped to IBM's heavy hex lattice, where each qubit represents a decision variable. And so after multiple runs, the quantum computer returns a distribution of sampled solutions, which is shown in the histogram. So from there, we select the solution with the best performing configuration. So in short, the QAOA algorithm efficiently searches a very large solution space much faster than the classical methods can. And then we have the parameter tuning process for the QAOA, specifically how our beta and gamma parameters evolve across each iteration. So beta 1 and beta 2 control the mixer Hamiltonian, which determines how the algorithm explores different possible solutions. And then the parameters gamma 1 and gamma 2 control the cost Hamiltonian, which evaluates how good each solution is based on our optimization objective. So as the iterations progress, you can see that these parameters, they sort of begin with large fluctuations, but gradually stabilize, especially around the 15th iteration. So this stabilization indicates that the quantum circuit has converged towards an optimal or near optimal configuration by minimizing the cost function effectively. So in other words, this tuning process helps the hybrid optimizer to find the best balance between exploration and exploitation within the solution space. And then to solve the routing problem on a quantum backend, we have the circuit architecture used. So on the left, we have the horizontal lines, which represent, each of those lines represents a qubit. And then the sequence of blocks corresponds to quantum operations applied during the algorithm. So the red Hadamard gates represented by H initialize the qubits into a superposition, which allows the circuit to explore all possible route configurations simultaneously. And then we have the blue and the purple gates, which represents the cost and the mixer operators. And so these encode the problem constraints and guide the system towards lower cost configurations. And then finally, on the right panel, we have the measurement layer, where the qubits, rather at this stage, they collapse into classical states, and then they are measured to represent the potential route configurations from which we go on to select the best performing one. So essentially, this circuit is where the quantum part of the bilevel model is executed by mapping our optimization problem directly onto the quantum hardware. And then to evaluate the performance of the optimized routes, we have several accessibility and efficiency metrics that were used. We have, first of all, the detour ratio, which measures how much longer the optimized route is in comparison with the original baseline route. So since it's a ratio, in this case, we want it to be as close to 1 as possible, which would indicate minimal additional travel distance. And then we have the Hansen Accessibility Index, which estimates how accessible each community is to their nearby bus stop. Then we have the Gini access metric, which evaluates equity across communities. So a value closer to 1 means that access is evenly distributed, while values closer to 1, a value closer to 0 rather means that access is evenly distributed, while values closer to 1 indicates inequality in accessibility. Then we have the mean walk time, which represents the average time that the seniors would spend walking to their nearby bus stop. And so this is, of course, an indicator of physical accessibility as well. And then lastly, we have the mean reachable stops. And then this measures how many stops are within a comfortable walking range, which reflects the overall service coverage. So these metrics, they capture both the system efficiency and the user accessibility, which allows us to assess rather whether the quantum-inspired model improves accessibility without compromising the route's performance. So now that we've gone through sort of the modeling and the optimization process, I'd like to move to the results section where we would look at how well the model balanced the two objectives of accessibility improvements for the elderly users and the efficiency of the optimized routes and what performance metrics reveal about its overall performance. So taking a look at the optimized bus routes compared to the baseline configuration for a maximum walking distance of 300 meters. On the left, you can see that the map of the optimized route. So here the blue squares represent the original stops, while the green diamonds indicate new stops that were added to better serve these age-restricted communities that are shown in red. Then on the table on the right summarizes the key performance metrics before and after optimization. So after optimization, we can see that the handstand accessibility increased from 0.142 to 0.547, which shows a major improvement in transit access. And then the mean walking distance was reduced by more than half, from 550 meters to 250 meters. And this it translates into a shorter and a safer walk for the elderly users. And at the same time, we can see that the route length doubled from 800 meters to 1,600 meters, and introduced a few turns as well. So this reflects the trade-off between accessibility and efficiency. So however, even with this slight increase in route complexity, you can see that the overall system achieves higher coverage and greater accessibility as shown by the improved accessibility indicators. Then we can see the optimized route under a 400-meter walking threshold, which provides a slightly more lenient accessibility requirement than the previous scenario of 300 meters. So to the map on the left, we can see the optimized layout, and compared to the 300-meter case, the system needed to extend coverage further to meet this new threshold. And as seen on the table, the handstand accessibility improved more sharply to 0.65, while the mean walking distance dropped to 250 meters, confirming that the elderly users are better served. But the Gini coefficient increased from 0.5 to 0.26, which indicates a mild rise in access inequality, which is usually a typical outcome when optimizing for total accessibility. And then the route length also doubled, and the detour ratio rose to 2.0. So this means that the overall accessibility clearly outweighed the efficiency loss. And these results highlight sort of how adjusting the walking threshold influences both design and fairness. And this gives planners the flexibility to balance coverage with efficiency. So just after the results section, I'd like to focus on three main aspects. First would be how the framework improved accessibility. Second would be what trade-offs were observed between efficiency and equity. And finally, what implications these results have for real-world transit design. So first, in terms of operational and geometric trade-offs, the optimized routes became longer and included more turns. And this means that we traded route simplicity for greater coverage and better accessibility, especially for the distant senior communities. And then secondly, on accessibility, we can see that the framework significantly improved access for elderly users by adding more reachable stops. But there was a small rise in inequality, but this was due to prioritizing prioritizing areas without access that were previously underserved. So Overall, access became more balanced across the system. And then third, the mobility benefits were clear. We could see that the average walking distance and time dropped substantially, making it easier and safer for the elderly users to reach bus stops. And then finally, we can see that route directness and user experience remained largely preserved. So even with the longer routes, travel efficiency stayed acceptable, which showed that improving accessibility doesn't have to come at the cost of usability. And so in conclusion, just to highlight the main outcomes, the contributions, and a few future directions, we introduced a quantum-inspired optimization framework that effectively integrates both accessibility and efficiency in transit route design. The results showed notable improvements such as reduced walking distance and time, better coverage, and enhanced accessibility for the elderly users. But there were minor increases in the route length and detour ratio. But these were acceptable trade-offs considering the broader service inclusion that was achieved. So importantly, the QAOA, the quantum approximate optimization algorithm, demonstrated strong potential for solving complex multi-objective transit problems efficiently, even with the limited qubit count that is available today. So looking ahead, future work will extend this framework to larger real-world networks and explore like real-time hybrid quantum classical optimization, allowing for adaptive and even data-driven transit planning. Finally, I would like to acknowledge our team members who contributed very much to this research and the list of references that were considered in the work is given. And finally, thank you for your time and attention. And at this point, I think we'll be happy to take any questions.
Yeah, I want to thank Daniel for that detailed illustration of the modeling framework and some preliminary result using the quantum computer. So his work really highlight how the optimization and content formulation operate in practice. So I appreciate that. I also look forward the opportunity to work with ISL for some potential collaboration. For example, take a smart stop metro in our local Tallahassee dial ride service here. It provides door-to-door transportation for senior and individual with disability who need to reach to the medical appointment. The place like the Tallahassee Memorial Hospital, Senior Center, neighborhood clinics, and those medical center. The user often call a day or two in advance. So this is a reality right now. And the agency dispatch the vehicle according to those requests on the second days. So this is compared with those Uber and Lyft, this is extremely low efficiency for those people. So in practice, this system also face a multiple challenge. Many appointments like cluster in the same morning window, yet those vehicles may travel long empty miles between the distant pickups. So when a passenger medical visit runs late and it disrupts the entire schedule. For the transit agency, that means a higher operational cost because you know that's the direct ride, those vehicles, every trip they offer, it costs more than $50, but they only collect about $2 of their fare. So this means a huge financial for this. So for the rider, especially for older user who manage the condition, it has to be anxieties and long waiting and the missed appointment. So imagine the collaboration could happen for this challenging for the healthcare side, local clinic and community health network like the Florida Association of Community Health Center, which might share some scheduling data, which allow us to understand when and where appointment demand peak. From the transportation side, for our side, like transit agency, Stop Metro, Big Bend Transit, and Wakulla County Transportation, they can provide the log, trip logs, service constraint, and the vehicle data. This can tell the operational realities and the bus hour, the driver's hour, fleet size, and coverage limits. And from the computation side, our team can bring advanced modeling. First, bilevel optimization using the quantum computer, and so on. For the so this is from the policy and social science side. Collaborator could be like from the public health, nursing school, urban planning, transportation engineering, computer science. We can evaluate how these optimize the service and actually improve the healthcare accessibility and reduce those missed appointments and enhance the quality of the life for seniors. So this is what I thought, and I look forward any potential opportunity work together. Thanks.
Thanks so much, Dr. Guo and Daniel, for the presentation. So now we have a few minutes for question answering. I do see there's a comment posted in the Zoom chat from Jacqueline Brooks. Dr. Guo, do you want to comment on that?
Yeah, I saw Jacqueline, you posed a question that as an elder person, I felt recently on a broken sidewalk while walking more than 1 mile to get home and fractures my wrist. Yeah, I'm sorry to hear that. Yes, that's the true reality right now. We do have, like, I always talk to the Florida Department of Transportation. Our local state DOT do have a lot of office covering different aspects. Like we do specialize, have the public transit office, we have the traffic safety office, and we have the emerging technology office. But most of our office, they mainly focus on the vehicle mobility. They only look at the vehicle numbers, vehicle traffic flow, but very few research look at the pedestrian. Except for the safety office. So I'm quite sometimes I'm proposed to them like not only for the sidewalk, for some other micromobility user like the e-scooter, like the bike sharing, those micromobility system operating. Sometimes they share the lane with the vehicles. We might not necessarily, due to the roadway design, the limits, we might not have the space for like exclusive bus lane, exclusive bike lane, or exclusive e-scooter lane. Normally, those e-scooter users, they share the lane with the pedestrian. But those micro-mobility systems, they are operating extremely fast. Like it could be 30 miles, 40 miles per hour even, which can bring safety concerns. So I'm highly promote that such research should be implemented, funded by the FDOT now, should look at people, pedestrians walking on the sidewalk, walking on those pedestrian lane, and also micromobility user, how to better design those allocation of the lane, and along with vehicles, and how to ensure the safety concerns. So this is an urgent need. Thank you for pointing that out.
Thank you. Any other questions from the audience? So maybe I can ask some questions. Also, my first question is related to the necessity of using quantum computing for this type of research. Could you share the improvements of quantum computing in this computing of optimization of the route compared to traditional computing infrastructure? Either like in terms of the cost of using quantum computing and also in terms of the efficiency or sort of the other performance improvements over the traditional methods. If you can comment on that, that'll be great.
Yeah, thank you. That's a great question. So our standing point for using quantum computing is because it can bring the computational resource. So if you look at the literature review slide, that in a traditional classical computer, we have to solve the transportation network problem, which could be thousands of a link. And every link, whether we should design a transit stop there, it's a binary question, 0 or 1. So we have to go through every possible solution, every link, thousands of link, 0 or 1, and solve one by one. So that could take about simulation more than 10 hours, 12 hours to just solve a very simple classical Salesforce network. But if you are using a quantum computer, it can speed up to the power of n, that quite fast. And the speed could be like the square root of n. So that means every thousandth of a link, it have the potential, have a probability of 0 and 1. It can be solved at the same time. So it might just take a couple of seconds, and then we have the result being solved. But right now, you mentioning the correct things that the quantum computer still have a large error. Like no matter what platform, like IBM, Qiski, or any simulator, still have an error. So we need to delve into see every solution and why this error and how to fix this error still is ongoing the research. So that's why the reason it has not been widely applied yet. But for the fundamental research, I think it's a trend that's made using of the quantum computer, those advanced computing to solve those NP-hard problem.
Okay, yeah, that's great. Thank you. And also, I see that Mark posted a question about the whether you have taken the consideration of the type of bus stops into this framework.
Yeah, I saw my old friend here. Mark, thank you so much. That's a great question. Appreciate your participating in this meeting. So yes, that's a great addition consideration for transit starts. It could be like a single just sign. It could be like the with a transit station design, and it could be like a hub, like a multi-modal public transit system. It could be including like the demand responsive transit, fixed run transit, and if in the Miami City, like we can have a metro transit station like the subway system. So it could be like design. So we could by consider different types of the vehicle system operating and consider if we are assigning different kinds of transit station and how to improve the accessibility since using different types of transit stop will consume different working time. This is a great consideration in the future research.
Thank you. And also, can you share some more information about your potential collaboration with, with agencies and organizations such as you said, like some Tallahassee transportation systems. How easy or feasible it is to deploy or implement some of these algorithms into their route planning?
Yes, we do have a long collaboration with the local transit agency, Stop Metro, and also with the, serving the Florida Panhandle area, Big Bend Transit, serving the nearby the 1210 county. And we also have a connection with the Florida Association of Community Health Center. Those are the community can provide us stronger support for such research. And we might just need their scheduling data, for the trip data, service log, and vehicle data. We are able to work on the algorithm using the quantum computing quantum platform to help them to better planning for the vehicle scheduling problems. So these are the communities we can reach out, we can secure their support. And for the funding agency support, the most suitable program in the past is called Smart and Connected Community, which already archived by the NSF. Right now, it has a new program. It's called the CPS, Cybersecurity Program. It's called Connected Communities. So it emphasizes a lot with those community support and how to let this agency can really make use of your proposed methodology and algorithm. So this might be the most relevant program through the NSF. And also I have explored like the FDOT, they like public transit office, every year they fund some of the research proposal like on the diary problems, like the South Metro, like how to improving the efficiency of the demand responsive transit system, that is FDOT. And additionally, I think you are the expert in the health, accessibility healthcare side. I'm looking for work with you, like the NIH, that's the kind of research, since it's highly relevant on the elder user healthcare activities. And from our side, we can secure some of the operator agency to support that.
Yeah, that sounds good. Thanks so much. I think we have 1 more minute for question answering. Are there any other questions from the audience? And also, I want to first of all also thank Dr. Qianwen Guo and Daniel for giving this time for this presentation. It's very interesting, and also shows that how high performance computing infrastructure, quantum computing, can be used for solving some real world problems for older adults, which is wonderful. And at ISL, we do have a wide range of research programs across FSU colleges and departments. And we also are inviting speakers from outside to speak in our events. So one of the events is going to be happening in January 29th from Dr. Ken Langar from University of Michigan. The director for the health retirement studies will be traveling down here to Tallahassee and give us opportunity to meet and then to discuss a variety of the research. And Mark has another question. How much access do you have quantum computers? Is your time limited?
Yes, that's a great question. That is a good question. Daniel, could you answer that question? Since we explore several platforms, each platform will, right now is extremely expensive.
Yes, yes and no. So using the free account that I have, we have limited access time, which is usually about 10 minutes of quantum access. But I think through one of Dr. Guo's colleagues, who I believe is at the College of Engineering here, we have a different paid package, which gives us access to more computing time. And also, we've also explored with D-Waves quantum computers, which are also kind of unlimited with the paid access plan. And also, we also explored using the quantum simulator. So with a simulator, you have realistic noise, and it gives you sort of like a realistic alternative to try your algorithms, but with the advantage of unlimited access time. So yes and no, we have packages that give us limited access time, but we can also access advanced platforms that give us sort of unlimited access time.
Yeah, so far, this research hasn't received any agency funding yet. So it become extremely hard for us to pay for the computation resource. So we actively and eagerly seek any opportunity to work on some funding proposal and hope in the future we can broaden our research.
Yes, so I see another question that says, how many computers are there on campus? So just to clarify, the quantum computers are not here on campus, but I think what I was referring to was access to IBM's quantum computers with a paid package that gives us greater computing time. So it is IBM's quantum computers, but not here on campus.
Yeah, but our Florida State, that our College of Engineering is working on the plan, like building quantum computer in the near future. Right now, they formed a large team to applying for the grant supporting that.
Yeah, I know there's also quantum computing initiative of FSU. They can spend more than $10 million in this initiative. I'm just wondering if there might be some computing resources being created to enable this kind of research.
Yeah, this opportunity will be in the near future.
Okay. All right, I think we're over time already. Again, thanks so much, Qianwen and Daniel, for the presentation. And we'll make this recorded lecture webinar available online, and I'll send you a link. And also, Nadia will help create feedback form, and then we'll send you a feedback form to get feedback for this webinar. And thanks so much, everyone, for joining the meeting. We'll see you next time.
Thank
Bye,
you.
everyone.
My great honor. Thanks.
Thank you.
Have a great day.